Have you found yourself debating the merits of designing your landscape projects in 3D? Perhaps you consider 3D to be useful in your presentation to clients, but nothing more. Maybe you view working in 3D as something that can be easily cut if the design budget doesn't support it. While these views aren't uncommon to many in our industry, the truth is 3D not only transforms your landscape projects, it informs it to save time throughout the design process. I'm Eric Gilby, a landscape architect and the product marketing manager for the landscape industries at Vectorworks. In this presentation, I'm going to share why designing in 3D, especially with smart hybrid objects in Vectorworks Landmark, can assist you in design analysis or proof of concepts, viewshed studies, sunshade studies, quantity takeoffs, and meeting sustainability objectives, just to name a few things. So quickly considering the rationale for 3D and why not all 3D modeling is the same. We may all have seen pieces starting in 2D and finished in a real-time rendering solution like Lumion, Enscape, Twinmotion, and D5. This 3D representation is very telling visually, and it does help to sell your vision for a site. In this example with the video animation with people walking as you move through the landscape can also give you a great understanding of what the project will look like. But the challenge that we see sometimes with some of this virtual representation of the 3D model is that you don't necessarily get data out of some of that. So there's a need to kind of keep what you do understand about objects that are generating data and try to figure out a way to kind of get a little bit of both. So you get the selling standpoint from a virtual representation, but you still want to be able to capture that data from some sense. So we still see the need for plans and sections and being able to calculate from objects and those dimensional shapes. So this information is still attainable, but we just want to kind of recognize that we might not necessarily see this from those more surreal or post-rendering solutions like we just looked at. So one of the things that we understand with 3D is that 3D geometry can tell its own story. So when we think about area and perimeter and height and depth and things like that, those are pretty standard understandings of what geometry can tell its story on. But what about surface area? What about volume? What about the distance along an edge or the distance from one edge to another? Maybe even that depth and height relationship, that width and thickness relationship, the weight that something might potentially carry, the angle or slope that kind of goes along with the surface area, but really being able to perceive that angle or the slope or that gradient. And then ultimately things like perimeter. So when we understand that there's an opportunity for geometry to tell its own story, that gives us another reason why we would want to kind of potentially use 3D geometry in our projects, because as we start to kind of figure out the materials that we want to specify, that 3D object is going to tell its story. So there's this idea of working with smart hybrid objects that can even tell more. So besides the fact that the 3D geometry is there to tell its story, smart hybrid objects can use that and then some. So you can append other data to those objects. They can become parametrically controlled, which those parameters then tell their story, and then the position or layout. So when we are trying to understand where something starts or where something ends, or where something very specific needs to be positioned, it can tell that story. And then all of that geometric data that was there to begin with tells its story. So as you can tell, the information that can get reported to a worksheet really helps you a lot when you're trying to do opinion of costs, estimates, code compliance, other kind of analysis. All of these things I think are really helpful to understand how you can incrementally get more out of 3D just because you started using that in your design workflows. So we're going to start into the presentation where we kind of led off with the learning objectives. We're going to go directly into the terrain model. So if you have ever heard or never heard of terrain model, one of the things that we can all understand is that most sites have a ground surface and most sites have a changing terrain in their ground surface. And so this idea of understanding how we can virtually represent that terrain or the surface treatment could be very useful for us in this aspect of analyzing our landscape. So a digital terrain model, or a DTM that we in the industry would refer to it as, is it's a replication of a site surface. And in most cases, you would recognize that it could be a triangulated irregular network, or what we sometimes call TINs. It could also be a raster or a grid network. So you have this ability to see a surface represented in some form of tessellation that allows that to stay edge to edge or surface to surface, and how that kind of relates to each other in that connection of surfaces. And it allows you to kind of see what that looks like in the overall context. So how do we get this information into a terrain model network or some other kind of surface? Well, in most cases, you could get a 3D surface from some surveying and mapping techniques. Some like drones, being able to capture a LiDAR surface. Maybe it's photogrammetry, where the pixels are smart enough to know their geographic or surface position. You could also get some of this information from 3D points that you could capture from a GPS device, or something like a total station or an altimeter. Some level of being able to gather that information from elevations from the sites using something like this. And also, if you were making use of 3D polygons that someone or some agency has provided to you, maybe it's through GIS, maybe it's from a survey engineer, all of that information that could potentially be available can be helpful as source data coming in to create and inform your terrain model. So here's an example where a 3D point cloud could be enabled. So being able to do some sort of a scan that helps to generate a 3D point cloud, the 3D points can then be used to come in and create a terrain model. So what you'll notice here through an example of Esri Site Scan Manager is that you get the site scan, you get a software application that helps to manage what those points are, and then you can bring that information into your software to then create that tessellated or that triangulated network of surfacing. So those 3D points go to work to create that triangulation of that surface. And so in any sense, this is a really good source for terrain creation. Ultimately, if you even just had something as simple as a 2D plan that you could trace to create that into a 3D representation for your model, the benefit here is that you don't lose the 2D representation out of it. So as you've created this into a terrain model, as we see here in both the Civil 3D and the Vectorworks example, you still get a 2D representation of contour works. You still get a 2D representation of how the surfaces are looking. So this example that you see between the two helps you to understand that not only are you creating a 3D surface, but it still gives you that representation of a 2D. So this is one of the reasons why a digital terrain model could be very helpful, because of its hybrid representation. Now, the analysis side of this comes into play when we look at things like cut and fill, or elevation studies, like of going from high and low, or slope analysis studies, or even which way surface drainage might be flowing. And then ultimately, we like the idea of being able to visualize what we're doing with the terrain. And so having examples of visibility studies could certainly be useful as well. So here's an example I wanted to kind of hit off the ground with as well. So looking at an example here, this was done by Holcomb Norton Partners. They were doing a project in Montgomery campus at Auburn University where they were helping the architects achieve a grade calculation. And so they needed to get soil put into where the building was going to be installed, and they needed close to 40,000 cubic yards of soil volume to help meet this so that the building would become more accessible for those who would come in. This was seeking lead credits. So one of the things that they knew was that they were also going to have athletic fields showing up in this site. So they made use of their grading tools using their digital terrain model to allow them to capture this understanding of regrading it so that they would get their athletic fields, how much soil volume was going to be created from this excavation, and they recognized that they had exactly what they needed by the certain realm of grading technique that they used to approach this site. So in this case, they use their digital terrain model. Even though it looks like it's in a 2D sense, this is really performing 3D calculations off of both surfaces of the existing and the proposed terrain. So this allows them to understand the net volume change, which is your cut and fill calculation. So in this case, they were successful in being able to figure out how to create their athletic fields and create the volume needed to be able to help with the installation of their building. Now, we also see an understanding of how this could be analyzed using something like an elevation study. So here's an example of an elevation analysis showing from high elevations to lower elevations on a site. Color seems to be the easiest way to do this, but even getting that legend to be able to diagram and document what those lower and higher elevations represent allows you to not only visually see the changes from low to high, but also that ability to see the data that's associated to it. So what elevations are we talking about, if it's the darker green or if it's a middle green? Um, so this example here that we see is a really strong example of being able to understand, using your terrain model, how to analyze it for this as well. So adding to that, the ability to see surface drainage flow. So which way would surface be creating runoff, and which way does that surface runoff collect? And then when you start to make changes, it allows you to see potentially two different colors. Like we see here, there's a red color for existing and blue color for proposed. Allows us to kind of see what the changes are that we are making to the site, and whether or not we are actively pushing water into our retention pond, or if we're missing it, we need to do some other grading techniques to get it in. So this is a very strong case for us to be able to use our digital terrain model to make sure that we are not draining into the neighbor's lawn, we're not draining directly into our structures, we're creating positive drainage, or we're actually able to manage stormwater in the best way possible. All of these ways of being able to analyze that terrain model would be very helpful here. So slope analysis. So we can understand the slope analysis as well through color ranges. So we can identify this with the ability to see from shallow slopes to steep slopes, whether or not we have drainage issues, and we have very low slope categories that we need to do something to kind of amend that, or if we have high slope categories that allows us to understand where we might need to still do something else to remedy an erosion concern. But ultimately, we could see, well, what does regrading a site look like in order to put our new facility and all of the surrounding elements in that new facility? What does that look like once we've regraded it? So you can make use of your slope analysis for pre-development and post-development analysis. And also for accessibility. One of the things that we note oftentimes is, whether or not the site seems to be accessible for those with differing abilities. And one of the things that you can identify even before you start doing development is what parts of the site are already accessible, if they happen to have an accessible surface. So another thing that I like to do with terrain models is to understand through visibility of what the view shed might look like. So using the terrain model to aid in visibility studies is great because you can highlight the terrain surface. You can make use of 3D views or try to enhance something or screen something with that topography. So it allows us to visually recognize through that terrain surface what seems to be visible at certain elevations, or what would someone see if they were looking from one vantage point to another. So I've set up a little example here. So we've got a commercial development that we'll be looking at, where the first idea was we've got a lot of terrain, or a lot of volume that's come out of this site. We need to figure out what we might want to do with this. And we start to think, well, maybe we could create this 30-foot high berm over on the side, and maybe create some sort of visual screen between the other things that are seen on the site versus what we would like for them to see. We want to control some of this. So we want to try seeing what the terrain model might actually create when we look at this view. So here's an example when we go into the software and we start to create some form of modeling here. We've got our terrain model. We create a 3D view that goes from one side looking into our site through the model or through the berm. We identify that our view height might be about 5.5 feet off the ground, and we're starting to look somewhere else at a normal perspective. And very quickly we see, oh, the only thing we see at this elevation is the berm. So we might even want to kind of come up to see, when does it matter what elevation we're at when we can start to see what's going on with the site? Well, you might agree that having a 30-foot berm seems a bit, kind of intrusive. It actually might be a little overkill and actually very, very expensive when we had to think about putting that much soil in that space. And then, you know, did we actually get the aesthetic value out of it that we had hoped? Well, putting ourselves at the top of that berm might uh, cause someone to wonder, all right, well, if we are at the top of the slope looking into the site, what would we see from this point? And it gives us the ability to do a little bit of a walkthrough and kind of understand what that berm at that massive height would entail. So in most cases, someone might come back and say, this does not seem to be the way that we want to approach this site. It just seems too um, intrusive on our project. So maybe we'll look at another example where we could do this more efficiently. So we do another example here where we're working with a 10-foot berm and some plantings on top of that 10-foot berm. And then we start to look to see, using the same conventions, we're going to set up our 3D view, looking from one side of the berm to the other. And this time we only need to be 11 foot off the ground on the furthest side. And we start to see, oh, we see the berm, we see the plantings. We don't necessarily see so much about the project on the other side, which is great because, it's managing our screen very well. And if we came in to be, somewhat on top of that mound or a little bit edging on the mound, we could see, oh, we definitely see things once we've come to the other side, and the berm doesn't seem to be all that oppressive. So we have this ability to see a 10-foot mound with plantings on top as potentially a better solution, and it allows us to see that this is probably more cost efficient as well if we had to kind of total up the cost of the plants in a 10-foot berm versus the 30-foot berm with no plants. So moving along from the terrain, we're going to go into sun and shade studies. And this is probably one of the more obvious opportunities that we have to look at what 3D can do where analysis is concerned. Because without 3D, you can't really do the sun and shade study. But it is one of the bigger reasons why we would want to. Because in most cases, a client is going to want either sun or shade, depending on the situation of how a site's going to be used. And so making use of this is very important. So this isn't something new. People have been doing solar studies for quite some time. In fact, this image here is an example of a physical representation of a heliodon or a sun study. So the heliodon tool, in its original case, was a physical tool that studied sun and shade on physical models. So it gives anybody who had the means to be able to get one of these tools to be able to see what their project would look like during certain times of the day and whether or not it was going to become energy efficient or capture sun and shade on their site wherever they needed it. So this is the example why this became important. So there's several tools out there that can capture this. So solar studies with software, the examples that I'm going to share with you are Enscape. This happens to be what they call sun settings. In Lumion, it's called Sun Effect. In Rhino, it's called the Sun Tool. In SketchUp, it's called the Sun Path. Twinmotion is called Daytime, and in Vectorworks, we call it the Heliodon. And there's other plugins that do this as well. So if you had some of these other more general tools and had plugins involved, you might see that they have plugins that enable you to see sun positioning throughout the day or throughout the year. So one of the things that I think is helpful to understand is that we may not be on that project site at all the given times that the client would like to kind of have that shade or sun exposure throughout the year and throughout those different times of day. So it's beneficial for us to go ahead and set up some of these models so that we can test those proposed shade structures or shade amenities or sun exposing amenities. And this means that as we start to study it, we can revise it as it's needed. And then once you have it set, you can show this to the clients with a lot more confidence, being able to represent how that 3D structure that you've created can actually provide the relief or the exposure that they were expecting. So here's an example where a firm like McGregor Coxwell did this in an urban space, and they were looking for a space on the site that didn't already have some form of shade throughout the day. So they were using their 3D model of the urban context as well as their park to be able to design something very contemporary. But notice that the shade and sun is giving some artistic treatment where they are looking at things on their project. So not only does the shade canopy itself have some contemporary uh, artistic treatments, but so does the sun and shadow. So when we see the shadow effects in here, it kind of reminds us of a dappled tree canopy shade, but it also gives us a very contemporary artistic look. So it kind of gives a unique treatment to the site. So they were making use of the Helidon in their software to be able to do this in a very, very cognitive way and an artistic way, so that not only are they achieving the shade that they were expecting, but the artistic treatment is verified as well. So here's an example where sun and shade studies can determine sun-heavy and shade-heavy areas for planting. So this was done by a designer named Danilo Maffei, and in his practice, he likes to put in not only the studies for different times a day, but he might also incorporate multiple suns in one file. So as you can see here, he's incorporated 4 different sun objects. This sun object happens to give them throughout the day where that shade footprint, or if you want to call it the shade print, would be, so that he can understand which plants would be better suited based on the shade that either the buildings or the existing trees might give, so that throughout the day he doesn't have to be out there throughout the whole year. He can use his model to kind of study this and understand what parts of the year and what parts of the day seem to provide the most shade and most sun for the sites to be able to do proper planting design. So the solar energies can also, or solar studies can also be helpful for energy efficiency goals. So as we start to look at examples here, we see a building that doesn't have a lot of plantings around it being completely exposed by the sun, and seeing different times of the day just to kind of make sure that throughout the day that this is accomplishing the sun and shade effects that they were looking at. So it allows them to understand, well, what changes if they put more plantings up by the building, and we start to see examples where the building or the plant material is starting to create more shade along the building, but it's also creating shade along the surfaces, making that space a lot more comfortable and a lot more temperature controlled. So even if they didn't have as much shade on the building itself, the overall capacity of the shade is reducing the temperature of the space, which then helps to reduce the urban heat island effect. But ultimately, it does still allow them to see whether or not they need to create other shade structures or other kind of shade interventions to be able to help further protect the building. Okay, so these solar studies can be very useful. You see some examples here on some urban projects, and also some examples where 3D perspectives are concerned, but also the ability to recognize smaller courtyard spaces, or even the idea of that hillside that we were just talking about, what kind of avenues we have in a city park or a city public space, even on rooftops, being able to understand what the sun and shade studies would look like on top of these buildings. So we have several different ways that we could envision what this solar animation or the sun studies would be able to do. And again, this happens from sun up to sundown. It happens from the beginning of the year to the end of the year, and it really provides not only the analysis but a visualization to help not only study but also help to convince our customers that we are implementing the right solution for their project. So this ability to add 3D workflows is important, because the ability to understand what the 3D addition to our workflows means is, a lot of people will say, well, adding 3D to our projects doesn't seem sensible because the client isn't paying for it. It takes extra time, all these kind of scenarios. I'm just not familiar or comfortable with 3D. I'm more familiar with 2D workflows. So this ability to add 3D really is not as arduous as you might expect. So let's see some examples about what this might look like. So generally, the idea is creating a shape and doing something that we jokingly in the industry call pushing or pulling. And it's really the same kind of idea no matter what software that you're looking at that does 3D modeling. It's push-pull in SketchUp, it's push-pull in Vectorworks, it's push-pull in Rhino, and it's press-pull in AutoCAD. So as you start to kind of think about what 3D workflows are about, you start off with a 2D shape. Well, that's what we've been talking about to begin with, is that 2D shape is already kind of our our start of our workflow anyways. So as we start to do other kind of project workflows, it's just a matter of starting with the same geometry, but you're doing a couple more steps like pushing or pulling them into conforming into that shape. So here's an example where one of my colleagues has created a very quick tutorial on making use of the 3D geometry access here in Vectorworks, but allows you to create the 2D geometry, extrude it, which is our push-pull method, and then allowing that to become that 3D geometry that then gets repeated. And so we see a very quick recognition of how to make that 3D geometry into something very telling, like this very simple sun arbor. And then similarly, one of my colleagues, Peter Summerlin, has created a little tutorial that you might find on YouTube that allows you to see how you can start with the 2D geometry from AutoCAD, bring that into SketchUp, and allow you to kind of see this recognition of 2D implementation into the 3D visualization treatment. So even though this one doesn't go extremely far into the whole design process, you'll see it's just a process of understanding what 2D geometry has created faces, and then what those faces then can do when you get ready to turn that into something visualized in 3D. So being able to do some representation in 3D gives you some tolerances for those face treatments, which ones seem to be closed, which ones seem to be open, and then once you see them, it allows you to just start to grab some of those faces and start to make your 3D push-pull methods so that you can very quickly start to visualize what these buildings will look like, what these elements inside your landscape would look like. So this ability of generating 3D from those 2D drawings is already there. So it's just a matter of grabbing that information and starting to visualize it. And the next step is to start talking about what other 3D elements are going to start to visualize. So in this example, we see the next step for him would be bringing in the plants, and what would those look like. So just this idea of taking that 2D geometry and turning it into something very easily visualized is the scheme here that I was trying to go for. Okay, so one of the things we understand is that oftentimes you might decide that you'll start to do 3D once you're committed to that 2D plan. Well, in some cases, if you're working with a hybrid workflow, that isn't necessary. You can create the 2D element and make it 3D and start to understand what you're already developing, and you didn't have to spend that much more time creating that 3D element out of that 2D element. So that means that as you continue to make changes, you didn't have to wait for the plan to be almost finished to start visualizing. You could start visualizing from the very beginning. So this idea of extruding or pushing and pulling can continue to something that we refer to as extruding. So instead of pushing and pulling, you might try something like extruding along a path or following me. So depending on the tool of choice, you might have different conventions where it takes that profile of something that you've created, that 2D profile, and then the 2D path that allows you to then take both of those elements and turn it into something 3D and visualize like we see above. So here's an example where a pull edge with a pull coping is starting to visualize, and you start to see very quickly, because you already had those 2D elements, how quickly that can become visualized into what that pull coping would look like. The benefit out of this is that that geometry remembers the length. It remembers its information. So if you're making use of software that allows you to keep that information, that's going to be bonus, because that allows you to understand, not only do I get to see what this looks like, but as I get ready to report how much coping I need, that extruding along a path will allow me to understand how much of that coping I really need to get put into the pricing, or how much material needs to get ordered for that project. Okay. Another example is by parametric modeling. So we saw the push-pull, we saw the extruding. Now there's going to be this idea of modeling in similar scopes. We still see this idea of taking a 2D geometric shape, but doing something with it that is a little bit more scripted, or a little bit more settings oriented. So we see this idea of user-defined things. So here's an example where you might be able to create some sort of a object, in this case a tapered extrude from this object, and then that object could have parameters like height and the angle that gets that element kind of formed to a smaller shape at the top, Whatever those dynamics are, it allows you to kind of see what those settings can do. So it's a little bit different than pushing and pulling, but it's taking push and pulling and setting it up as a script or a setting. Okay, here's an example where we create a tapered extrude where again you've got the Z or the elevation height of this object and see that transformed based off of those parameters, and very quickly that object has more information, so it knows how tall it is and it knows what that angle is on it. So if you need to get some of that information reported, the object knows it. Now it gets even more interesting when you get something that's a little bit more parametrically controlled. And notice in this case, this is an example that Vectorworks has, so it's beyond just the idea of a tapered shape. Now this tapered shape is going to have other elements. It's going to have a height, it's going to have the shaft, it's going to have a capital or some sort of a cap, and it's going to have a base. So that information is something that we would have wanted to have known anyways. So how much material would we get out of this object if it was even more parametrically controlled? In this case, it happens to be a column. So if you're creating something like this, imagine that it might take you a little bit more time to create some of these settings and the parameters to make it. But once you have, these objects are easier to change afterwards. So if you selected this and you made changes to the height, you made changes to the width, you made changes to the base or the cap material, those parameters means that those changes are more immediately made. So the con is that yes, you have a little bit more time than setting up just a push-pull and those kind of 3D treatments. But the pro out of this is that you now have that information out of that object that can report on itself, but the revisions are made so much easier. And we know that a lot of the work that we're doing has revisions involved, so why fight it? You understand that being able to get back into that object's parameters and making just a couple adjustments and seeing what those results are means that your changes are made so much faster. Okay, so another efficiency is made in the symbols. So parametric objects are made into symbols. So this ability to see that same idea where those parametric objects can be repeated, but ultimately we see an example here where this post and rafter that we see in this pergola, very unique, very custom created. 3D modeling is at its height here. There isn't anything other than the parameters making this that is making it any more intelligent. But by doing that, we now have created this object inside of a symbol. And that means that if we wanted to change that symbol from, let's say, one type of material to another, that's made more easily. So once we make it there, then the rest of them are made. Okay, so we're going to get into this section talking about harvesting your 3D data. So being able to get that information back out of those objects, whether they're smart or just plain geometry, we have this ability to get that data back out of it. So when we start down this road, understanding that 2D plan data is still available is really important, because you might not necessarily model every single thing in your file, but you might. So if you did, that 2D geometry is still there. Even though you might have modeled your edging like we see here, that 2D data of its perimeter or its overall length is still capturable. You can still get that information that you did not lose just because you might have turned it into a 3D object. But we also notice that the ability to see 3D data gives us more information. So if we're creating let's say a green roof in this case, or an elevated paver system, we now have information from all of those objects that help us to do more information about the overall green roof. So you can capture area, you can capture length, you can capture volume, and you can capture weight, because these objects have components or they have other 3D geometry that's a part of that object. So let's say if it's a landscape area or hardscape or some other kind of componentized object, that means that we can capture its area, as we see here in the chart. We can capture volume if it has information that's associated to the volume, like the gravel or the growing medium. But in all senses, we can actually get linear feet. If that's the only thing that we needed to get out of this object, we can get that out of it too. But the next benefit here is that you have the ability to capture your details much quicker. So you can have that ability to not only see it visually and also get the understanding out of it through your reports, but you can take a slice through it and see your details happen so much faster than if you had to redraw them on your own. Okay, where we're talking about harvesting water. So harvesting data is important when we're doing this as well. So 3D allows us to get surface area of the rooftops or other kind of capturing devices. That allows us to get slope. We also have the understanding if we had slope on other surfaces, what that runoff would generate. And that allows us to then generate how much volume we're going to need when we capture that water or other kind of elements. In most cases, I'm going to expect it's water. So when we figure out how much volume of harvested water we have, do we have a some sort of catchment device or vessel that is large enough to hold the water that we expect to capture from this? So that 3D data allows us not only to understand the capturing side of things, but it also allows us to understand the storage side of things. So it allows us to kind of verify if our storage devices equate to what we expect to capture. So another example here is where using other elements, so we have a digital terrain model in conjunction with a landscape area, in conjunction with worksheets that allow us to use the complicated computations that we would use for stormwater runoffs and the ability to understand the runoff coefficients that we have with certain areas on our site that also get different classifications based on their slopes. So we had this ability to make use of all three of these objects to help calculate a stormwater management plan, as we saw here from Gray Leaf Design. So what we next see is the ability to see how this 3D data not only gives us the analysis, but it also gives us an understanding of visualizing what's coming, but we also see that volume for the retention could potentially be captured even from just the terrain information. So you have 3D geometry that's telling you the information of what difference is between the two surfaces, but we also see that the two surfaces could also represent the water board or the highest elevation of the water, and then help to calculate how much volume that this retention pond might carry. So this information can be very useful as we continue to use that 3D geometry to get that information from. Another example we see from PCLD, or Pacific Coast Land Design, they made use of 3D to help them with IFC models. So as they were doing BIM collaboration with architects and storm water and civil engineers, they were able to understand how much gray water that they could capture besides the typical rainwater that was coming to the site. And so they were making use of the 3D geometry from the IFC files and their 3D model to be able to understand how much water was going to be captured, how much landscape needed to be supported, and if they had enough water being captured to be able to support that. And what we also notice is that it allows them to visualize what things would look like once they've captured this. So at that point, you have 3D not only visualizing things, but it also helps you to use the 3D geometry to do a lot of this data calculation that then allows you to help tell the story, win the project, understand whether or not you are achieving sustainable goals. All those kind of things can happen because we use this 3D data to be able to help analyze. So with that, I am done. We certainly invite you to email us and contact with any question that you have. Thank you.